Hi everyone. So in this video, I'm going to talk about regression diagnostics. It is very important that you run these diagnostics when you're fitting a regression model, like especially a simple or a multiple linear regression. Um, so remember that when we fit a model, we make certain assumptions. We assume that the error terms in the model or the residuals are independent, identically distributed, and they are normally distributed with a mean of 0 and a constant variance of sigma squared. So we have to make sure that those assumptions are satisfied. So the first assumption that we are going to look at is checking for homoscedasticity, which means you're checking for constant variance. Do the residuals that you get, or are they really do they really have constant variance or not? Because that's one of the main assumptions. If the variance of residuals is not constant, then the residual variance is called heteroscedastic. There are graphical and non-graphical methods to detect heteroscedasticity. In this video, I will just go through most of the methods, mostly which of them are mostly graphical ones. So a commonly used graphical method is to plot residuals versus fitted values or predicted values, that is residual versus y hat. So to plot, this is the code. Let's say you fit a model and you call, so throughout the video I'm going to assume that your model object is called model, right? When you fit the model, you call it, you give it an object name, and that object name is model. So model dollar residual versus model dollar fitted values. You can add a horizontal line. Now these residuals, as you can see, they should not show any sort of a systematic pattern. A most common pattern that you would see if there is any sort of heteroscedasticity is that they will look like funnel shape. So this graph, if it has a funnel shape, that means there is the constant variance assumption is violated, or if it has any other sort of specific pattern going on. Right now this graph doesn't show, for example, this graph doesn't show any sort of pattern, so this is fine, as the assumption of heteroscedasticity, homoscedasticity is fine here. Then the next assumption is that you're assuming that the residuals are normally distributed. So many researchers, they believe that multiple regression requires normality. That is actually not the case. Normality of residuals is only required for valid hypothesis testing. That is, normality assumption assures that the p-values of the t-test and f-test will be valid. So I often mention in class that when you are fitting a regression model, the objectives can be, it can have two different objectives. The objective could be that you are interested in finding whether there is an association between y and x, and if it is statistically significant or not. And if that is your objective is some sort of inference, right? So then in that case, you must check for normality assumption. On the other hand, the objective of regression could be prediction. You just have a specific value of, for a specific value of x, you want to predict y values. In those situations, you really don't need the normality assumption. You can work without that too. Normality is because normality is not required in order to obtain unbiased estimates of regression coefficient. If you recall, in the mathematical stats course, we talked about talked about finding the estimates of betas, that is the regression coefficients, using least square estimation, and then we did not make any normality assumption there. And those least square estimates are same. The estimate that you get, they are same as the maximum likelihood estimate, but they really don't need any normality assumption. So it is not required in order to obtain unbiased estimates. So you're fine if your goal is prediction, but if your goal is estimation or testing, then it is not fine. Then you must make sure that the normality assumption is required. So to test the normality, what you can do is you can Graphical, there are tests. There are theoretical tests like Shapiro-Wilk test and several other things you can do. But I'm just going to concentrate on graphical techniques because they're pretty good. So for testing normality, you can do a QQ normal plot of residuals. That is normal quantile versus theoretical quantile versus sample quantile plots. Now, theoretical quantile, you're going to assume they're coming from normal. And if the sample quantiles line up with that, that is, if they all fall on that line, which kind of here most of them are, there are few point outliers out here and few here, then the assumption of normality is met. Another way, there are several ways, like you can plot a histogram, you can plot a box plot to see if there are of these residuals to see if they are normally distributed or not. Then another assumption is important because remember we assume that they are independent, right? The residuals are independent. So a simple visual check would be to plot residuals versus time variable. So, but in many data, you don't have time variable. It's not time series. Therefore, what you can do is you can use ID number. So for each row, assuming that each row represents one row of the data for a specific subject, or it could be, let's say, school or a college. So each row represents something, right? A specific thing that is of interest to you. So it has an ID number. So you can plot it against ID number as an ordered variable for the data. So this is the code that you would use. D or data dollar snum. Snum is that subject number, school number, or whatever that is for you. Residual plot versus ID number. And then it should not again it should not show any sort of seasonal or time, like if it was time series it would have shown some sort of seasonal or trend. In this case it would just basically show some sort of trend if they are not independent, but this one is seems to be fine. So those are the three key assumptions that you have to check. That's part of the diagnostics of regression. In addition, there are few other things that you want to check. They don't have anything to do with the assumption, but you must make sure that that is not happening in your regression model. One of them is checking for multicollinearity. What is multicollinearity? When there is a perfect linear relationship among predictors. So let's say you are regressing y on x, y, and z. So an x, y, and z have some sort of perfect linear relationship. The estimates of regression model cannot be uniquely computed in that case. The term collinearity implies that two variables are near perfect linear combination of one another. When more than two variables are involved, it is often called multicollinearity, although the two terms are often used interchangeably. So the primary concern is that the degrees of multicollinearity increases the regression model estimates of the coefficient become unstable, and their standard errors for those coefficients can go widely inflated. So one way of detecting that is using variance inflation factor, we call it VIF, to measure the degree of multicollinearity. As a rule of thumb, a variable whose VIF value is greater than 10. So the rule of thumb is that a variable whose value is greater than 10 may merit for further investigation. Tolerance is defined as the inverse of VIF and is used by many researchers to check on degrees of collinearity. A tolerance value lower than 0.1 is comparable to VIF of 10. It means that the variable can be considered as a linear combination of other independent variables. So in R, we can use VIF from package car. So whenever you are doing these diagnostics, these are the two key packages that you want to install. Most of these diagnostic tools are available in the package car. Since there are two packages, so you install them and then you just call VIF for that model and it will spit up the variance inflation factor for all the independent variables. Anyone which has more than 10, that means you need to investigate it further. So that's one thing that you should check for. The other thing is model specification. A model specification error can occur when one or more relevant variables are omitted from the model. For example, I've seen in many of you have the model where your x, the beta 1 is significant but statistically significant, but your R square adjusted is very small, indicating that there are more relevant variables that are actually missing from your model. If relevant variables are omitted from the model, the common variance they share with the included variables may be wrongly attributed to those variables, and the error term is inflated. On the other hand, if the irrelevant variables are included in the model, the common variance they share with included variable may be wrongly attributed to them. So model specification errors can substantially affect the estimate of regression coefficients. So there are many methods and statistical tests to check whether or not a variable is relevant in the model. To visualize, so because we are concentrating on visual measures, so to visualize the effect of each variable in the model, we can use added variable plot called a partial regression plot. The added variable plot is a scatter plot of residuals of a model by excluding one variable from the full model against the residuals of the model that use the excluded variable as dependent variable. The slope of simple regression between these residuals will be the same as coefficients are excluded. If the slope is not close to zero, we conclude that the variable is relevant to the model. Added variable plot is also actually useful in you seeing influential points, and you can do that using AV plots in model. So that's how you would do that. If you are interested in more about it, you can always email me and we can talk about it. Then one more thing, and last, like one of the few things that you must check is linearity. You are fitting a linear model between y and x. Does it even have a linear relationship or not? So to check so what you do is you check linearity of residuals. To check this linearity, you plot residuals against fitted values as well as the predictors. If any of these plots show systematic shapes, then the linear model is not appropriate and some non-linear terms must be added. In package car, the function residual plot produces all these plots. Also can be used to test for this can also be used to test for linear model versus do you really need to add a quadratic term for each variable, that is test for curvature. So all you need to do is install package car and use this command residual plots and inside provide the object name, that is the object, the model that you have fitted. Then another thing that you should look at, so remember when you're doing diagnostics, you're checking for model assumptions, that is linearity, independence, and normality. And then the other diagnostics is you check for multicollinearity, you make sure that you don't have too many independent variables which can be linearly related, right? Which could be linear combination of each other. You also want to check if the linearity, if there is any linear association, like you want to check the linearity assumption, linear relationship between y and x, if that is even possibility or not, right? Otherwise, what's the point? Or you probably need to add curvature to it. Then another key thing to remember is unusual or influential data points. Sometimes you'll get some extreme observations. They will pull your slope of the regression in a totally different direction. A single observation which is substantially different from other observations can make large difference in the results of your regression. There are three ways that an observation can be unusual. Outlier. An outlier is an observation with very large residual. In other words, it's an observation whose dependent variable value is unusual given its values on the predictor. So your y value for this is very different than other values. Then there are leverage points. Observations with extreme value on predictor variable are called leverage points. Leverage is a measure of how far an observation deviates from the mean of that variable. These leverage points can have an effect on estimate of regression too. So this is like when you have extreme x values. Influential points. An observation is said to be influential if you remove that observation and it changes the estimate of coefficient substantially. Influence can be thought of as the product of leverage and outlierness. If a point has a very different y and x value, of course it's going to influence the slope. So now there are different tons of tests, like the people have written books about just these unusual and influential observations. So I'm not going to go into too many details, but at least one of the things that you can easily check and must check is studentized residuals. They can be used to identify outliers graphically. In R, we use R standard to do that. We should pay attention to studentized residuals that exceed plus minus 2, because when you're studentizing them, basically you are standardizing them. And so if they're standardized and they're not normally distributed with a standard normal distribution, most of the observation, 95% of the observation, should be within plus minus 2 standard deviations, right? So anything that is above that and or above plus minus 2.5, and if it goes beyond plus minus 3, you should get alarmed, right? Because that's not a very usual thing that should happen. So these results here, you can use you can get the studentized residuals, and then you can actually identify what is the school subject number or whatever you have used as an identifier. And this is the little code. So first you find the studentized residuals. You store them in a vector called res.student. Then you plot that vector. Um, and then you add horizontal lines -3 to +3 to identify any extreme value that is beyond those lines. And then you find out which data point is outside that 3 standard deviation cutoff. Then you use index is a row numbers of those points. You find out which is greater than 3 or -3, and then you add subject or school or whatever identifier you're using. In our case it is school, for example, or subject number, so we're denoting it by snum, to have extreme values. When you print them, it gives you some index number, and then you can print the name of the points, the subject or the school name or whatever identifier you're using, of the point that are outside the bounds. In our case, 211 is the most worrisome observation, for example. So the row observation of row number 211, then you can go back and revisit and see what it is, what's going on with that, maybe just remove that and then fit your data points. So that's pretty much it. I have added the reference here. So when I post it, I will post this Word document too. You can always visit this website for further details, or feel free to email me. So I'm going to stop here and I'll see you guys in a different video.